Yes, hello and welcome to another video on apply electricity. Okay, um, it's Dr. Osman Hassan, your apply electricity lecturer. So we are going to continue from where we stopped, right? We stop at question 30, right? So we continue from there. Okay, question 31. Question 31. So continue from question 31. Here, question 31. A conductor carries a current of 8 amps at right angles to a magnetic field having a density of 0.5 Tesla. Calculate the force on the conductor. So this question, okay, as we are going to see, the questions from question 31 to 60, right? All the questions there are based on chapter 6 to 8, right? So mean chapter 6, 7, and 8. All the questions there from 31 to 60, they are from those 3 chapters. So start with this. We have 31. So from this, we can see that we are giving current, which is 800 amps. We are also giving the flux density, that's magnetic flux density, which is V here equals to 0.5 Tesla. Then we have been told the angle, right? The magnetic field and the conductor, they are at right angle to each other, right? Then what else? So yes, so this is what we are giving. Well, if you see that what is missing here, we don't know the length of the conductor. So there was an issue with this question. Okay, so but the length was supposed to be close to 1 meter. 1 meter, supposed to be 1 meter. So it's supposed to be a conductor of 1 meter. So here's supposed to be 1 meter. Conductor of 1 meter of length. Okay? So it's supposed to be a conductor of 1 meter of length. Carries a current of 800 amps. So the length here, but it was given as a bonus question, right? But so with this question, the force which is going to be acting on the conductor is going to be equal to the product of these 3 parameters, meaning the magnetic flux density times the current times the length of what? The conductor. But here, and then we multiply it by the sine of the angle between the magnetic field and the conductor. And we have been told here that the conductor is at right angle to the magnetic field, meaning the angle between them is 90 degrees. So theta here is 90 degrees. Okay, I think I solved this similar question under the other past question as well. So it's similar one. So we can just replace this one. Magnetic flux density is 0.5 times current 800 times length, which is 1, times sine what? 90 degrees. And this will give me here 400, right? Times here 0.5, okay? Here 0.5. Yeah, 0. Okay, I've already done that. So now here we times 1. Sine 90 is 1. So you can see that we get 400 newtons for this. So the answer here will be 400 newtons. Now moving to question 32. Question 32. What is the magnetomotive force required to produce a flux of 0.015 webers across an air gap 2.5 millimeters long, having an effective area of 200 centimeters square? So here we are interested in the magnetomotive force. That's mmf, right? mmf, right? Which is the same as Fm, right? The magnetization force. And the formula for this mmf is going to be equals to, we know mmf is equals to, in terms of what? The length, right, of the conductor exposed to, like, of the conductor, or the mean length of what? The magnetic material that we are talking about, and then times the what? The magnetic field strength, right? So mmf equals to HL. Okay, HL. So based on what we are given, right, you can see that we are given the magnetic flux density. We are given the magnetic flux rather. So we are given magnetic flux, which is 0.015 webers. Then we are also given the mean length, right? Meaning the mean length here, which is the air gap. So we have an air gap. So that's the medium that we are dealing with. Air gap, and the length L is 2.5 millimeters. So we get this. Okay, now we are now to find the mmf. So you can see that we are given the length. So what I don't know is the what? The magnetic field strength. So how do I find the magnetic field strength? You can calculate the magnetic field by writing this formula. If we take the magnetic flux density over the magnetic field strength, that will be equal to what? The absolute permeability, right? Absolute permeability, which is going to be equals to relative permeability of the material that we are dealing with, or the medium. Here we are dealing with air. So relative permeability of air times the permeability of free space, right? Times this. So this is a formula. When it comes to air, the relative permeability of air is 1, right? So I'm just going to make the magnetic field strength here, the subject straightforward. So we get H should be equals to this. Here is 1, right? We get 1 here. So that becomes right, so you get this over the magnetic flux density over the permeability of free space. So you get this. Now you can see here that we are the magnetic flux density, right? We don't know the magnetic flux density, but I didn't write this. Even if you look at the question, you can see that having an effective area. So we are given the cross-sectional area, right? So meaning from here I can even get magnetic flux density equals to flux over what? Area. So with this, I'm going to get the flux is given as 0.015, and then the area is 200 centimeters square, right? Area, I didn't write it, but area is 200, let me just write it straightforward, centimeters square, right? So that means 200 times 10 to the power minus what? Minus 4. Okay, minus 4. So let's do this calculation. So I'm doing the calculation. So I have 0.015 divided by 200 times 10 to the power minus 4. So you get this one to be 0.75 Tesla. So you get the value to be 0.75 Tesla. Now that we've gotten Tesla, I can now find the magnetic field strength by taking the flux density, which is 0.75, over the permeability of free space, and it's a constant value, and the value is 4 pi times 10 to the power minus 7. Okay, minus 7. So this value is going to be given. It's normal giving. I think it's even up here. Let me show you this value here. It's given. So now what do I get? Now we can take 0.75 divided by 4 times pi times 10 to the power minus 7. Okay, and we get so we're going to get 5596831.04. okay, amps per meter, right? Amps per meter for that. Now that we've gotten this, we have been asked to find the MMF. So we come and replace our magnetic field strength in the formula for calculating the MMF. So MMF now be equals to this value here, 59681.04 times the length, which is given from the question as 2.5 millimeters. So that will be 2.5 times 10 to the power minus 3. So I'll just multiply it by 2.5 times 10 to the power minus 3, and then we get the answer to be equals to 1492.08. okay, amps. The unit for MMF is amps, tenths, or amps. So we see that when you look at the answer is going to be A. Okay, so we get A for this. Now moving to question 33. A rectangular coil measuring 200 millimeters by 100 millimeters is mounted such that it can be rotated about the midpoints of the 100 millimeter side. The axis of rotation is at right angles to a magnetic field of uniform flux density. All right, this is question 33. Uniform flux density 0.05 Tesla. Calculate the flux through the coil when the 100 millimeter sides are inclined at 45 degrees to the direction of the flux. Okay, so this question here, so we have been given a rectangular coil, right? So if I have a rectangular coil, so let's say I have a rectangle of this nature, okay, then you have some wires around this. So maybe you have wires around this one, So this is a rectangle. Now, and the sizes and the dimension, we have 200 millimeters by 100 millimeters, right? So let's say we have 200 millimeters by 100 millimeters. Okay. Now it said it is now mounted, said that it can be rotated about the midpoint. So you can rotate this, right, at the midpoint of the 100 millimeters and 100 millimeter size. Okay, so the 100 millimeter side maybe here, where you can rotate this. The axis of rotation at right angles to a magnetic field of uniform flux density. Okay, so calculate the flux through the coil when the 100 millimeters are inclined at 45 degrees to the direction of what? The magnetic flux. Okay, so what this means is that, again, here we are interested in flux, right? And the formula in terms of flux and magnetic flux density is going to be, we know magnetic flux density is the what? Magnetic flux over what? Area. Okay, so if you look at this, the rectangular coil is now inclined at 45 degrees. So this question is quite challenging, right? But you have to understand this in terms of what? In terms of the force that is going to be acting a conductor, right? Similar to that of also even an induced EMF in a conductor, right, inside a magnetic field. So a similar concept here, right? So here, if you make the magnetic flux density the subject, you get what? Magnetic flux density. I mean, you are making magnetic flux the subject here. You get magnetic flux density times what? The area. Now, because it's now going to incline, right? So you are producing this flux, right? But now the rectangular coil is now inclined at 45 degrees. So that means you now take sine what? Times sine 45 degrees, right? So you get the flux. Once you get it, because it's now inclined, so that means the flux that is now going to passing through, right, is now at an angle. So you get 45 degrees. So with this, we can just write the magnetic flux density from the question is given as 0.05, and the area here is just the cross-sectional area of the coil, right? Okay, let me do this, right? So I have this 0.05. The area is just the dimension which are given, and the dimension, we have 200 millimeters by 300 millimeters. So the area becomes what? The product of the dimension. So we get 200. So we change that to meters. So that will be 200 times 10 to the power minus 3. Now times what? The other side, which is 100 millimeters. So that will be 100 times 10 to the power minus 3 as well. Then times what? The sine 45. Okay, so we get this. So this will give us our answer. So let me do the calculations. So we have 0.05. We can even reduce this, right? I can reduce this because 5 here, that will be 5 times 10 to the power minus 2. Right? 1, 2, minus 2. And then this part here, this is 2 times 10 to the power 2. 2 times 10 to the power 2. Here will be 1 times 10 to the power 2. So that when you add the powers, so we have 2 minus 3, that will be minus 1, right? Plus 1, that will be 0, then 2. plus 1, sorry. So here we 2 minus 3, which is minus 1, minus 2, right? Sorry, plus 2, that will be plus 1, minus 3, so that will be minus 2. So we have here to be 2 times 1 times 10 to the power minus 2 here, times sine 45. So we get here 5 times 2, which is 10, right? So 10 times 10 to the power minus 4 sine 45. So I have here to be times, you can have just multiply this straightforward, right? So now it's taking much time. So I have 10, this times 10 to the power minus 4 times sine 45. So you get 7.07, okay, 1 times 10 to the power minus 4, and then this is what Weber's. So we get this answer. Now with this, you can see the answers, possible answers, they are expressed in milli, right? We have A is 1 milli, then B is 0.01 milliwebers, then 0. So you change this into what? Milli as well. So milli, that will be what? So you change this, so that will just be 0.71 times 10 to the power minus 3, right? Which is 0.71 milliwebers. So we get the answer here to be C. Now moving to question 34. A coil of 200 turns is wound uniformly over a wooden ring having a mean circumference of 600 millimeters and a uniform cross-sectional area of 500 millimeters square. If the current through the coil is 4 amps, calculate the magnetic field strength. Okay, magnetic field strength here. So from this question, okay, you can see here question 34, right? Question 34. Based on what we are given, you can see we are given the number of turns n, which is 200. Then we are also given what? The mean length, right? Which is L. The mean circumference, mean circumference length, which is L rather. That will giving us 600 millimeters. Now the next quantity that was given is the area, which is 500 millimeters square. And we are now, if the current through the coil is 4 amps, so calculate the magnetic field strength. Here again, current, which is 4 amps here, right? Okay, now with this, if we are to find the magnetic field strength, we know that MMF, right, or just FM, they are all the same. So let me use FM this time. It's equals to what? The number of turns times what? The current, right? The number of turns times the current. And at the same time, FM is also equals to what? HL, right? The magnetic field strength times the what? The length, the mean length. So you see that with these two here, we can equate them. So that means that I can make HL the subject, which is going to be equals to Ni over what? L, right? So with this, I can get the magnetic field strength to be equals to the number of turns, which is what, 200, times the current, which is 4, divided by the length, mean length, which is 600 millimeters. So that will be 600 times 10 power minus 3. So this will cancel here. I have here to be 3. So 3 divided by 4, that is 0.75. No, sorry, it's 4 divided by 3, rather. So let me, 4 divided by 3, that will be 1 point something. 4 divided by 3, that will be 1.33. So with this one, you bring it up, you bring the negative up, so that will be 10 to the power 3. So you can see that will be what? That will be 1.3 kilo amps per meter, right? So when you look at the possible answers that we have, so when you look at the so when you make this, you 3 times 1, 2, 3, so that will be 3 amps per meter. Because when you look well, you realize that the answer here, this corresponds to what? A, right? The possible answers that are there, this is equals to A. Now moving to question 35. A coil of 200 turns is uniformly over a wooden ring having a mean circumference of 600 millimeters and a uniform cross-sectional area of 500 millimeters square. If the current through the coil is 4 amps, calculate the flux density. So you can see it's similar to question 34, right? But this time we are interested in the flux density. Again, flux density, which is flux, magnetic flux over what? Area. So you can see that we don't know the flux, but we know the area. So with this question, we can use this formula which I wrote earlier again. I wrote this one before, which is if you take the magnetic flux density over the magnetic field strength, is equals to what? The absolute permeability, which is relative permeability times what? The permeability of free space. But here you can see that we are talking about what? A wooden ring, right? We are talking about wooden ring. So when you have a wooden ring, the wood is what? It's a non-magnetic material, right? Magnetic material. So as a result, the relative permeability is going to be equal to 1, right? It's going to be the same as that of what? The relative permeability of air. So because we are dealing with the medium here, which is what? Wood, and wood is what? A non-magnetic material, the relative permeability will be what? 1. Okay. So you can see that if we do that, we can now find the magnetic flux density with this. So let's make magnetic flux density the subject. This implies will be equals to, now we know this one is 1, so we just have the the permeability of free space times the magnetic field strength. So I will just have this, which is, again, this is a constant, 4 pi times 10 to the power minus 7 times what? The answer we got here, which was 1333. So you have this 4 times pi times 10 to the power minus 7. So that will give me this one, right? Then times 1333. So I'll get 1.675 actually, times 10 to the power minus 3 Tesla, which is going to be, so we use this one. So this is the answer I got. But we are interested in the what? If you look at the question, we are interested in the question 35. Yeah, we are to find the magnetic flux density, right? We are to calculate the magnetic flux density. No, that was this in the, magnetic flux density. Okay, question 35. Okay, oops. So we have to find the magnetic flux density here. And I've gotten 1.67. So is there a mistake here that we didn't take into consideration? 1.67. Let me see. Okay, so here we got the relative permeability of this thing to be 1. So we have 4. Let me do this again and use a 1330 here. 4 times pi times 10 to the power minus 7. Okay, minus 7 here. Times what? 1330 here. So I'm getting here to be, okay, yes, so I've gotten here to be 1.67 milli, right? 1.67. okay, when you look well, I think that will, here you can see that this is expressed in what we have, micro, right? We are getting the right answer. Is that the expression here? The expression in micro Tesla. So if I was to express mine to in micro Tesla, so let's see with this one, that will be, now you move here back 3 times, so 1675 times 10 to the power minus 6 Tesla, which is 1675 micro Tesla. So you can see that the answer here becomes C, right? The answer here becomes C, which is 1680 micro Tesla. Okay. Now moving to question 36. So question 36 here was given as a bonus because it's incomplete, right? So I'm not going to even look at this. This was incomplete. So the same for question 37. It was also incomplete. The permeability, the absolute permeability or the relative permeability of the material, it wasn't given, right? It was not given. So question 36 say bonus, 37 to say bonus. Now moving to question 38. Question 38. Let me enlarge this a bit. Question 38. A magnetic circuit comprises 3 parts, 1, 2, 3 in series with the following. We have one, a length of 80 millimeters and area 50 millimeters square. Then the second part, a length of 60 millimeters and area 90 millimeters square. And the third part, an air gap of length 0.5 millimeters, and then area 150 millimeters square. So a coil of 4000 turns is wound on part 2. So remember part 2 here is wound on part 2, where the length is 660 millimeters and then area 90 millimeters square. And then the flux density in the air gap, right now we are talking about the air gap, which is part 3, is 0.3 Tesla, assuming that all the flux passes through the given circuit, and that the relative permeability of part 1 and 2 is 1300. Okay, so here you are asked to what? So that's a preamble, right? This is a preamble question. Now we go to question 38. That was a preamble. Referring to the preamble above, find the MMF of part 1, 2, and 3. So to find the MMF of part 1, 2, and 3. So here, because we are dealing with material, right? So this is a composite question. So you have a material, and it's in what? In 3 parts, right? So let's say part 1 here, 2, and then 3. So when it comes to what? The MMF, right? So if you have current passing through this, the MMF, the magnetomotive force, is going to equal to 1. MMF here is going to actually equals what? The MMF due to each individual part, right? So we have H, let's say this part 1, HL, L1, HL, sorry, H2, L2 plus HL plus H3, L3, right? But here we are not actually we are not even asked to find the MMF, right? But you have to find the MMF due to each part, right? So you are just to find this. Now to get each part, right? So let's start with if you look at the question well, it's become easier to get the third part, right? The third part, because if you look at the third part, which is the air gap, we are dealing with air gap here. We have been told that the flux density in the air gap is 0.3 Tesla, right? So meaning for the air gap, we have a flux density of what? 0.3 Tesla, right? And I know that if I'm to find the MMF, the MMF for the air gap is going to be equal to what? Meaning the magnetic field strength of the air gap times the mean length of the air gap. So you can see that with this I can get the magnetic field strength of the air gap by using this formula, right, which we wrote earlier. So since we are dealing with air gap, the relative permeability of air is what? 1. Relative permeability is 1. So we just get this one to be equals to the permeability of free space, right? So we get the magnetic flux density of over the magnetic field strength equals to the permeability of free space. So with this, the magnetic field strength due to the air gap is going to be equals to, meaning 0.3 Tesla times 4 times pi times 10 to the power 7. So here, let's calculate this. So that will just give me 0.3 times 4 times pi times 10 to the power minus 7, right? Minus 7 here. So this is going to give me, we get here to be air gap. Here is going to give us 3.767. Okay. Let me just make this 7. Okay. Times 10 to the power minus 7 amps per meter. So that will be for this. But now we can go ahead and now calculate the MMF due to the air gap, which is going to be equals to what I wrote here. I wrote the formula already here. So we just get this to be H is now what's the value here. So we have 3.77 times what's the length, which is given in the question, right? Which is 0.5 millimeters. So 0.5 times 10 to the power minus 3. So this will be times 0.5 times 10 to the power minus 3. So you get 1 point. Okay. I think there is an issue with this. Where did I make a mistake? Let's look at this again. Check again. Because I'm getting 1.88. There should be a mistake with this. Okay, let's just cross check a bit and see. So with this, we are having, let me see. We know the magnetic flux density of the air gap is 0.3 Tesla. Okay. So, and then so we are dealing with air gap. So we have a permeability of free space. So let me do this again. Probably there's so it will be 0.3 times 4 times pi times 10 to the power minus 7. Okay. Yes, so we get 3.75. And the mean length of the air gap is 0.5. So this times 0.5 millimeters times 10 to the power minus 3. Okay. Here we are getting the answer to be 1.88, right? 1.88 Tesla. Okay. 0.3.75. Okay. So we are dealing with air gap, which is 0.5. So 0.5 millimeters, an air gap of 0.5. Okay. We have this. Okay, we have current. Okay. So here, I don't know what the problem is. Okay. Wow. This question, we have the magnetic flux density of the air gap is 0.3. The magnetic flux in the air gap is 0.3 Tesla. Okay. 0.3 Tesla. Okay. So I made a mistake here. It's this place. Okay. Oops. let's say mistake here. The formula when you make it the subject, you get what? It should be the magnetic flux density divided by the oops, it's here, right? This here will now be equals to magnetic, you are making this over this, so that is supposed to be 0.3 Tesla, or divided by 4 times pi times 8 power minus 7. So we get here to be 0.3 divided by 4 times pi times 10 to the power minus 7. Okay, so here now supposed to be 0. Sorry, it's 2.36. Okay, so now you multiply now by 0.5 times 10 to the power minus 3. So you get this way. So once you've done this, you're going to get 1.178. So if you get this, you get this answer times 10 to the power minus what is the problem? I don't know. It's like keep on encountering some issue with this question. Okay, let me do the final one. 0.3 divided by into brackets 4 times pi times 10 to the power minus 7. Okay. Wow. So times, so here is wrong. Times 10 to the power. Okay, whole of this, right? Okay, let me just write everything. So like I'm doing it separately. So the formula, let me be this times HL, so that I will do it straightforward. So that I'll just have 0.3 times divided by 4 pi times h power minus 7 times 0.5 times h power minus 3. Straightforward. So once I'll get times 0.5 times 10 to the power minus 3. Well, so now we've gotten it finally. 119.37, okay, amps. Okay, we got this answer. So you can see that with this question here, if you look at the possible answers, right, we have for the part 3 is the one that we calculate, the MMF. So you just look at the last part and correspond and compare with our answer. You can see that C here is we have 11.9, B is 1.19, C is what? 119 plus 0.3, which is what we got. And then you can, so because of the, we don't even have to calculate the other ones. So the answer here will be C. In order to save time, you don't have to calculate for the other one. Referring to the preamble above, estimate the coil current to produce such a flux. So since we know this is the right answer here, right? So you are asked to find the coil current that will produce this flux. And to find the current, we know that MMF But here, this will be what you can say. You can even call this one here the total mmf, right? Total mmf will be equal to the number of turns times what? Current. And the total mmf will be the sum of what? The individual mmf. And then we already know C is correct. So we just mean their mmf, they are what? Correct. So I'll just come here, calculate for the mmf, the total mmf rather. Total here, which is going to be the sum of what? Question answer C, right? So I have 44.1 plus 18.4 plus 119.3, 4.1, right? Plus 18.4 plus 119.3. So you get this answer. So we get this answer here to be the total mmf to be equal to 181.8 amps. Once I've gotten this, I can now replace it in the formula. So making this current the formula, I get total mmf over what? Number of turns. So that would mean that means 181.8 divided by 4,000. That's the number of turns. So the current becomes this, you have by 4,000. So you get 0.045 again amps. So when you look at the possible answers, so if we were to, they are in millimeters, they are expressed in millimeters. So you express this in milliamps. Okay, you express your answer in milliamps, you get 45 milliamps. 45.45 milliamps. So the answer here becomes what? C. Now moving to question 40. The total flux in the core of an electrical machine is 20 milliwebers and its flux density is 1 Tesla. Calculate the cross-sectional area of the core. So here again, we've used this formula several times. You are asked to find the cross-sectional area. That is question 39. Here, magnetic flux density is magnetic flux over what area. So you can see that we are giving what? The magnetic flux density, which is 1 Tesla. The flux, which is 20 milliwebers. So we make area the subject here, so that we get area will be equal to magnetic flux over magnetic flux density. So this becomes magnetic flux, which is 20 milli, so 20 times 10 to the power minus 3, and then the magnetic flux density is 1 Tesla, so 1 here. So we are going to get what when you divide this? So you get 20. Okay, that will be just 2, right? 2 times 10 to the power 1 times 10 to the power minus 3. That will be 2 times 10 to the power minus 2, which is 0.02 meters square. Okay, so the answer here becomes B. Okay, so we get the answer to be B for this question. So we have here to be B. Now moving to question 41. Magnetic flux density is measured in, so the unit that we have been using for magnetic flux, you can see that it's Tesla, right? So it's D, Tesla. If the total flux in a magnetic circuit is 2 milliwebers and the cross-sectional area of the circuit is 10 centimeters square, what will be the flux density of the material? So this is question 42. You can see that question 42 is similar to again 40. We are now given the flux, magnetic flux, then the area we are asked to find the magnetic flux density. So we just magnetic flux over area. So that is the magnetic flux density, flux here is 2 milliwebers, so meaning 2 times 10 to the power minus 3 over the cross-sectional area, which is 10 centimeters square. So 10 centimeters square will be equals what? 10 times 10 to the power minus 4. Okay, so you do the multiplication. This one is now going to be, here will be minus 3, right? Minus 3. So this minus 3 will cancel. So you just have what? The answer here to be 2 Tesla, right? So when you look at the possible, we have B, which is what? 2. So we get the answer here to be 2. Refer to the following data to solve question 43 and 44. A coil of 100 turns is wound uniformly on a wooden ring with a mean circumference of 1 meter and a uniform cross-sectional area of 10 centimeters square. The current in the coil is 1 ampere. So that's the preamble. Now we have to use this preamble to solve question 43 and 44. Question 43. From the data above, what is the MMF and the magnetic field strength? Right? So this is question 43. Now, if you look at the question, so you talk about MMF, we have to find MMF and the magnetic field intensity, which is magnetic field strength. So based on what we are given, you know MMF, right, is equal to the number of turns times current. So if you look here, well, the current here in the coil is 1 ampere. So we know the current. Then the number of turns is also given as what? 100. So this part here just become 100 times 1, which is 100 amps. So that is MMF. Now let's get the magnetic field strength. We know that MMF is also equals to what? The magnetic field strength times the length, the mean length, right? So if I know MMF, and from this question we are given the mean circumference. So the mean circumference is the same as the length, the mean length here. So we make magnetic field intensity the subject, we get MMF over what? The mean length. So this becomes MMF, which is 100, divided by the mean length, which is 1 meter. So 1. So we get 100 amps per meter. So this becomes question, when you look here, that becomes question C. Okay, so this will be question C. Moving to question 44, still using the preamble. From the data above, calculate the magnetic flux density and the magnetic flux. So this time we have to find magnetic flux density and the magnetic flux. Now, to find the magnetic flux density, which is similar to the question that we even solved, the previous question. Question 44. Magnetic flux density over the magnetic field strength is going to be equal to what? The absolute permeability, right, of the material that we are dealing with. Here you can see that we are using a wooden ring, right? A wood is what? It's a non-magnetic material. So because of that, its relative permeability is going to be what? 1, right? So we go absolute permeability of the wooden wood, which is going to be relative permeability times the permeability of free space. But since it's a non-magnetic material, so it will be, the relative permeability is 1. So due to that, we are just going to get the magnetic flux density to be equals to the relative permeability, the relative permeability of free space times the what? The magnetic field strength. So you just make this one the subject. So that becomes 4 pi times 10 to the power minus 7 times h, which is what we just calculated to be 100. So when we look at the possible answers, so we can see that we have what? They are maintain them in 4 pi in some of them. Okay, when you look well, so for example, if you take 4 times 100, that will just be 400, right? 400. Or you can even look here. If this is 100, mean that will be 10 raised to the power what? 2. So we can write 4 pi times 10 to the power minus 5. Right. 10 raised to the power minus 5. And that will be for Tesla. But if you want to make it in terms of micro, right? Micro Tesla, that will be, meaning that will be 40, right? 40 pi times 10 to the power minus 6 Tesla, 10 to the power minus 6 Tesla. So that will be 40 micro, right? Tesla. So we get there to be this answer here. So when you look at the possible answers, you can see that we have D, which is 40 pi micro Tesla. So okay, though that's even the only one that is right, the only 40 pi micro Tesla that we get. So from this we can even go ahead and know that it's going to be D. But let's get the magnetic flux, right? The magnetic flux as well. Once I've gotten the magnetic flux, which is going to be equals to, from this you make this a subject, right? So that will be what? Magnetic flux density times area, and then the magnetic flux density, which is 40 times 10 to the power minus 6. Then the area is giving us what? 10 meters square. So 10 times 10 to the power minus 10 centimeters square. 10 times 10 to the power minus 4. So when you multiply this, remember here is 40 pi, okay? 40 pi here. So we can maintain the pi so that we get 40 times, okay, even with this, right? It will just be, again, 40 pi. And this one we just add them. So this will be minus 6 plus 1, that will be minus 5 minus 4. That will be what? 10 to the power what? Minus 9. Minus 9 meters. So this one too, right? You can change this to micro 2 as well, right? Micro Weber. So that will be, now we want to make here to be, so that will be 10 times minus 3, then times 10 to the power, 10 to the power minus 9 here. Here with 10 to the power minus 3 times 4 pi. So you see that we get Tesla to be equals to we get the magnetic flux density from this will be equals to 0.0, right? You move it 4 pi micro Webers, right? So this become our answer. So this becomes, so you can see that we've gotten what these answers, right? This is 4 pi. So here the answer becomes D. Okay. Now moving to question 45. Which of the following is not true, right? So the reluctance of non-magnetic material is comparatively high, right? Yes. So when you talk about a non-magnetic material, the reluctance is high, meaning resistance. Remember we said is reluctance is a resistance to the equation of what? Establishment of magnetic field in a material. So if it's a non-magnetic material, meaning the reluctance is high, meaning it has a higher resistance. So A is correct. B, the energy loss due to hysteresis is greater for harder magnetic materials than for softer materials. This one too is true, right? If you are dealing with hysteresis, right? If you are having a hard magnetic material, it tends to have what? The energy loss tends to be higher, right? Because of the hysteresis loop. Yeah, you're going to have a very large hysteresis loop. And for a softer magnetic material, the hysteresis loop tend to be small, which is, so it is tend to also to have a very low it tends to have a very low energy loss, right? The energy loss is actually low for softer magnetic materials. Then C, the remanence of a ferrous material is measured in amps per meter. So this one we haven't even done remanence on this, but we know that magnetic field strength is what? The unit is amps per meter, right? So you can see that is now being associated with something, a different parameter. Absolute permeability, then the absolute permeability is measured in what? Henries per meter. This one is correct. Absolute permeability is Henries per, is relative permeability, which is not having unit, right? So the unit for absolute permeability is what? Henries per meter. So that's correct. So the answer here is going to be C. That's the one statement that is not true, right? Now moving to question 46. The current flow in a 510 coil 1 on an iron is 4 amps. The reluctance of the circuit is 2 megahenries. What is the flux produced? So here question 46. So we are interested in the reluctance. What is the reluctance? Okay, this question here, we know that again MMF or FM is equals to Ni, the number of turns times current, but at the same time to magnetic flux is equals to FM over what? Reluctance, right? So if we were to make reluctance the subject, you get here to be what? Fm over magnetic flux. And then this just becomes Fm, which is Ni over magnetic flux. So here we are given the number of turns to be 500. The current is given as 4. Then the magnetic, we are rather asked to find the magnetic flux, right? So we are to make, we are to make the flux the subject here, right? We have to make the flux a subject, so meaning here flux, we don't even have to, in that case, just use this formula straightforward. So I'm having now this formula Ni yes. So here it's just 500, right? The number of 500, current is 4 over the reluctance of the circuit is 2 mega, meaning 2 times 8 power 6. So here we get here to be 500 times 4 divided by 2 times 10 to the power 6. So here we get 1 times 10 to the power minus 3, which is 1 milli. So the answer here becomes C. Moving to question 47. From the following list, match the magnetic quantities with their equivalent electrical quantities. So with this question 47, right? So when it comes to this, for example, if I have electrical quantities here, electrical quantities, then maybe at this time we have magnetic quantities here at this side. So when it comes to this, so when we talk about current, for example, you have current, the corresponding magnetic quantity is what? Flux, right? If you have FM or MMF, right? The corresponding electrical quantity is going to be voltage. So here's MMF, right? When it comes to resistance, the corresponding this will be what? Reluctance, right? Magnetic parameter of quantity will be reluctance. So based on this, if you use that, we can see that for the first part we have what? Current, then meaning the corresponding magnetic quantity is going to be what? Flux. So if you look at the possible answer, we have what? A, so meaning A and then D here, right? So and then if you look at, we have AD here, this one AF, so it's wrong. We have AE, is wrong. So we have A and D. That's the remaining answers that we are checking to see which one is correct. Now we go to the next one. If I take reluctance, that one, the corresponding quantity is going to be resistance, so that means F. So we have AF. Yeah, it's going to be resistance, right? So we have BF. So here is BF. So the answer here becomes A. Okay, we get this one to be A. Becomes A here because we have AD, then we have what? BF, which is resistance. So I don't have to go further. The effect of an air gap in the magnetic material is to in question 48. So if I have my air gap in there, what does it do? Well, this question, air gap, right? We have A increases the reluctance. So if the formula for reluctance in terms of air gap is going to be with the permeability of free space, right, times area. So you can see that if the air gap is what is there, the reluctance tends to be higher. Why? Because this is what, remember, is 4 pi times 10 to the power minus 7, right? So it's very small, so it's inversely proportional to the reluctance. So because it's small, it's always going to give you a higher reluctance. So if you have air gap, you tend to have an increased reluctance. Okay, so yes, if you look at B, divide the flux, right? The effect of it is to divide with the flux. No. C, reduce the flux density. Now it's not going to reduce the flux density, right? Then we look at reduce the MMF. No, it's not going to reduce it. So the answer here becomes what? A. Now question 49. A conductor carries a current of 10 amps at right angles to a magnetic field having a flux density of 500 millitesla. If the length of the conductor in the field is 20 centimeters, the force on the conductor is, so here we just have to use the formula for force, which is magnetic flux density times current times what? The length, right? And we have been told that the conductor is at right angle to the magnetic field. So this we have sine 90. The angle there is 90. So that we have this become 1. Now I can just multiply the 500 millitesla by the current 10 amps, then by the length, which is 20 centimeters. So I have this. Let me multiply this before. So I have 500 times 10 to the power minus 3 times 10 times 20 times 10 to the power minus 2, right? So here we end up getting 1 Newton. So the answer here is 1. Question 50. In a horizontal conductor, current is flowing from left to right, and the direction of what? The surrounding magnetic field is from top to down. The force exerted on the conductor is going to be, so we look at question 50 here with this question, right? Question 50, the answer here is going to be C, right? So if the current is flowing left to right, the direction of the surrounding magnetic field in the top, right? The current, the force on this is going to be what? Away from. So it's going to be C. This one is in the handout. You have to read the handout. You understand this. Now, question 51. The force on an electron traveling at 10 raised to the power 7 meters per second in a magnetic field of density 10 microtesla is 1.6 times 10 to the power minus 17 newtons. The electron has a charge of this. We didn't do this in class, but based on the formula that we wrote here, right, you can infer on what the force, right, is similar to this formula that we just wrote. But instead of what? Conductor, right, we are dealing with now what? an electron. So the force is still going to be this, meaning that you take the magnetic flux density. Now, since it's an electron, we are going to use the what? The velocity of what? The electron, right? The velocity of the electron then times what? The charge, right? Okay, so this becomes the formula for this. We are interested in getting the charge, so we make charge here the subject, force over the magnetic flux, and then the velocity. So charge will be equal to force. The force is giving us 1.6 times 10 to the power minus 17 newtons over the magnetic flux density, which is 10 micro, then the velocity, which is 10 to the power 7. So if we do all this, so let me take, so here we can even just do this, right? Yes, 10 to the power 1 here, now 10 to the power 1. So here will be what? Minus 5, right? So here become minus 5. Minus 5 plus 7, that will be 2. So you take the 2 up. So you just get 1.6 times 10 to the power minus 19 here, coulombs, right? Because we are there. So the answer here becomes C. When you look here, answer becomes C. Now moving to question 52. For a current carrying conductor lying in a magnetic field shown in figure 1, the direction of the conductor is, again, this one too is in the handout, right? The diagram here is in the handout. So with this, the direction of the conductor is going to be what? Downwards, right? So this one is in the handout. So we get D to be this. Now question 53. An electric bell depends on, so we are talking about electric for its action. So if you are having an electric bell, it's going to be what? Depend on what? A permanent magnet, B, a reversal of current, C, a hammer and a gong, D, an electromagnet. It's going to depend on an electromagnet, right? Because we are dealing with electric bell for its action to take place. And so this one is done. So question 54. In the hysteresis cycle, the value of H, which is the magnetic field strength needed to make the intensity of magnetization 0, is called coefficient force. True or false? So here it becomes true. Okay. If you have an hysteresis loop, we saw this under the previous question that we solved, right? If you have the hysteresis loop, or you can say the curve, the force, right, or needed, or in that case, then what? The magnetic field strength that you need to what? To make the magnetic flux density 0. Magnetic flux density here is the same as what? The intensity of magnetization. That's what they mean here. Intensity of magnetization here is the same as the magnetic flux density. So the answer here is true. Now 55. There is a force of attraction between two current carrying conductors when the current in them is A, in opposite direction, B, in the same direction, C, of different magnitude, D, of the same magnitude. So here, if you have two current carrying conductors, right, and they are in opposite direction, so because they are in opposite direction, right, the magnetic field, right, that is going to be established in each of them, right? So if one is opposite the other, so the magnetic field is going to be, or you can say the poles, right? The poles are going to be what? Different, right? So as a result, the poles that will be on one of them, right? Let's say one is what? There's a current, right? Current conductor. So if the current is going, this is just example, current here. So let's say due to that, we have here to be what? North pole and south pole. Now if you have another conductor and the current is what? Entering this way. So you have north pole, here too is going to what? You are going to now have a similar case whereby here maybe now because of that you get south pole here, and then you have north pole here as well. So we get this. So here becomes south pole and north pole. So once they are going to, because they are in opposite direction, the current there is going to what? Attraction. So the answer here is A. Now moving to question 56. Figure 2 shows a rectangular coil of wire placed in a magnetic field and free to rotate about axis AB. If the current flows into the coil at C and if the current flows into the coil at C, the coil will, so we have the current flowing here to this. So as a result here, this, because of the direction of current here, so the rotation, because the current here is moving away from what? From the viewer. It's moving away from the viewer. So the coil will rotate, right, in clockwise direction. So the answer here becomes B. Okay, again this is in the handout. Okay, 57. The magnetic field due to a current carrying conductor takes the form of, if you have a current carrying conductor, the magnetism is what? They are always in what? A, rectangles, no. B, concentric circles. C, wavy lines. D, straight lines radiating outwards. It's always in concentric forms, the magnetic field around what? A conductor. In Fleming's left-hand rule, the thumb always represents direction of what? Magnetic field. No, that is wrong, right? So that is false. In Fleming's left-hand rule, the thumb indicates the direction of motion. Now 59. Fleming's left-hand rule does not indicate the voltage in the conductor. This is true. So when we use a Fleming's left-hand rule, we talk about what? We are talking about the motion, right? The magnetic field and the current. It doesn't include the what? The voltage in the conductor. This, in the Fleming's left-hand rule, the fourth finger always represents, this one again is a repeated question, right? Last, the previous year, the same question. Here, the fourth finger always what? Shows the direction of the magnetic field. So here is C. So this is what the end of today's video. So I'll stop here. We'll answer the next question later. Bye bye.